Now let's have a look at part B. We want to test at a significance level of 5% whether the housing expense is lower for these students. Now, we thought that they spent 650, so we said that under the null hypothesis, that's our just, regular claim that we always think is 650. But the new data shows up and apparently it seems to be less than 650. It's 615. So we think that this should be less than 650. Now, why would we test at all? The thing is this, in statistics, things can happen by chance. So we want to know whether this difference is big enough that the observation did not happen by chance. The observation did not happen by chance. And when we say did not happen by chance, it just means that if we take more and more observations of expenses on houses, most of them on average are going to be less than 650. So I'm going to go through that in a second once again. The difference is big enough that the observation did not happen by chance. Because you see, if we had, for instance, an expense of, let's say, $638, well, maybe if we take other samples and we take the average of expenses there, we're going to have somewhat around 649, 651. So the difference is not going to be large. This could happen just by chance. Just somehow that sample happened to be, with an average expense of $638. But if the observation is like really, really different, really, really smaller, then that probably did not happen just by chance. It probably happened because if we take consistent samples, we would have consistent averages that are less than 650 in most of the cases. And when we say that we tested 5% level, because statistics is never about 100% certainty, it's statistics, it's estimates, we're almost sure but never completely sure. When we say that we have a 5% level significance, all we say, because what's the significance level? That's the type 1 error, that's our alpha. Type 1 error equals to alpha equals to 5%. Let me change color because this is not very clear. Alpha says that we allow for a 5% probability of rejecting the hypothesis when we shouldn't. Now, what does that mean? It means that there's a 5% probability that our conclusion is wrong. We see an observation and we say that, yeah, it's significantly lower than 650. While in reality, that happened by chance. We shouldn't have said that it is a significant difference. So alpha is the probability of seeing a result by chance and therefore giving a wrong conclusion. Hope this makes sense. Now we allow for this 5% probability because, as we said, in statistics we cannot be 100% sure. We cannot ignore the fact that we can go wrong. But let's see if this observation is going to be so different that in spite of this alpha, we will still be, confident enough to say that this difference is significant. So how do we do that? We're basically going to use a t-test because we have sample data. We have the sample standard deviation and our sample size is quite small, it's 61. When we have relatively small sample sizes, usually below 100, we mostly use t-tests. When we have large sample sizes, we can use z-tests because in that case we have standardized normal distributions. But don't overthink about it at the moment. We'll have videos about that in the future. So at the moment, right now, all we can do is to see whether we have a significant difference by using a t-test where we take the difference between our observation, our average, from the population average that we thought we should have, divided by the sample standard deviation over square root of n. And the sample standard deviation divided by square root of n is also called the standard error. Just so you know, like in the future, sometimes you will see not s divided by square root of n, but just a number here. That number is the standard error. And what this value is showing that by how many standard errors is our sample average far away from the population average. That's what the t-value is showing. Now, let's actually compute it. This is going to be quite mechanical. It's just math. So 650.107 minus 650 divided by 124.695 over 61 equals to minus 2.19. Okay, that's our t value. Now how do we give a conclusion? Recall that we have a critical value. In every test we have critical values, and we're going to compare our value with the critical value. Let me zoom out so we have more space. So what's going to be the critical value here? Because it's a one sample test, so one sample test, we will have a critical value. One more thing that matters when we're checking for the critical value: what kind of test do we have? We have a one-sided test. The rejection region is going to be on one side, so we will have one tail of the distribution that we care about, meaning that we want to have a significance level of 5% on one side only. So 5%, and the degrees of freedom is n minus 1, and that would be the critical value of 5%. 61 minus 1 will be 60 degrees of freedom. If we look this up in the table, that would be equal to 1.67. Now, the t distribution is symmetric, so let's draw it. Let's draw it and see what conclusion we give. So this would be our distribution, t distribution. We see the critical value is 1.67. 1.67 is one critical value, but because it's symmetric, we also have a negative critical value over here, minus 1.67. Now, we said that the rejection region can happen on one side, can happen on the left tail, so all we care about is what's going on over here. And we can see that our value, our t value, is minus 2.19. So it's, let's say, over here. We can see that it is in the rejection region. So we reject the null hypothesis, which means that we have enough evidence, we're confident enough to say, to claim that the average expenses less than $650. So that observation, this average of 615, is different enough for us to say that overall the population mean should be lower than 650. Hope this makes sense. We are done.